What's up, Section 2-2, and I am thrilled. Hopefully you guys have stuck along with me and watched these lectures and try to learn as much as possible because, hey, we're finally here. I can't wait for it. Section 2-2 and beyond is like a different game entirely in geometry because now you kind of know how to play the game. What I mean by that is we spent the first 10 sections of the book basically teaching you rules of the game. What are the original definitions, the original assumptions you need to make, and a few of the original facts in order to prove more facts and prove more things about the world around us. So now I've shown you all that stuff. We've gone through it. You've taken notes. And if you've taken organized notes, you've done all your homework, I think you're in great shape. And I hope you find the next several sections a lot more enjoyable. So we're looking at today, Section 2-2, properties of parallel lines. Today, there are four theorems today. 3 to 4, I'm not exactly remember. But the more theorems, the more exciting that is because you'll be able to solve them, prove them. And right, I really think right now, and I hope you see, and I hope you can do this pretty quickly, geometry kind of just becomes a game now, right? How do you play this game of geometry? You know the rules. It took 10 sections to get the rules. And how do we splice and dice everything together so that any kind of fact or before it's a fact, it's a conjecture, right? How can we take a conjecture and really prove that it's totally a fact and know where it came from? So geometry is kind of like this machine. It's built a certain way. Euclid and other early thinkers built it out for us. And now we're going to have to get under the hood, right? Under the hood of the car and see what's going on, see how the machine's kind of constructed. And one of the biggest sections you're going to learn today is properties of parallel lines. When you have two parallel lines, and then you have a line, a coplanar line, that's coplanar with the two parallel lines, intersecting both of those lines, things happen, right? Things happen. And we begin with an assumption, and then after that, we're able to prove several things, and we'll be able to justify our logic today. Now it's all like the next several sections are just about justifying our logic, realizing how there are definite truths out there in the world and they can be justified. And that's one of the nice things about geometry is that there's so much noise and so much craziness going out there in the world. Geometry is a field, for me at least, that shows you that human beings have really been looking to figure out what truth is. How do you establish truth? How do you prove truth? And it's a very hard thing to do in most things you'll be interested in life, but at least there are some things in life where there are absolute truths that you can work towards. And one of those things is geometry. You can find some absolute truths here. So we'll get into it in a second. And I have some reading in front of you, and perhaps you're reading the section as well. But I wanted to point out to you that I don't know if I assigned you this problem of the last problem set, but it's kind of thinking that maybe you did this already. It says, by experimenting with parallel lines, transversals, and protractor in the last set of exercises, you probably discovered that corresponding angles are congruent. Okay, corresponding angles are congruent. So when you have parallel lines, only when you have parallel lines and a transversal, then corresponding angles will be congruent. If the two lines aren't parallel, then the corresponding angle is not congruent. But anyways, if you had the parallel lines, you did it. So hopefully you noticed that. If I sign that, if not, no worries. But that will be what we begin today with. So it says there is not enough information in our previous postulates and theorems to deduce that property that when you have two parallel lines cut by a transversal, that the corresponding angles are congruent. There's not enough to deduce, prove, right? That is a theorem. So that means we begin today with accepting it as a what? As a what? I look at you. We can't prove it as a theorem, but we want to include it as a rule. It's known as a, wait for it. We'll just wait for the next slide. Let's get into it now. All right, I bet you know what's coming first. Starts with a P, ends with an E. It sounds like past at the beginning and Ulet at the end. That's right, folks. And we're dealing with some corresponding angles. Yes. Corresponding angles is where we begin. Angle 1 and angle 2. Yeah, they're corresponding angles. And we know they're corresponding angles even though we don't know what yet about K and M. We don't know what about K and M. Well, K and M are coplanar, we know that, but we don't know that they're parallel yet. All we know is that we have this line T, and it intersects both of the lines in different points. So we know that this is a transversal here. So if you're transversal, we have some corresponding angles here. So we begin, right? We begin with saying if, okay? So I'm going to give you an if here. I'm going to give it to you that if these are indeed parallel to one another, we will be able to make what conclusion? What do you think? What do you notice about angle 1 and angle 2? Because we begin with an assumption. We begin with something that you notice. Angle 1 and angle 2, they're both obtuse. They look pretty alike. Yeah, you're right. They are congruent to one another. They are congruent. So if K is parallel to M, then angle 1 and angle 2 will be congruent to one another. That is our beginning conjecture, and it will remain as a conjecture. There's actually not enough. We haven't learned enough about geometry yet to prove something like this. So it turns out you need to assume something about parallel lines and transversals first before you can prove other things we'll get to later. So this is what it gets assumed in our book right now. So if 2, so let's translate this. If K is parallel to M, then angle 1 is congruent to angle 2. Let's translate this into more general words so that we can use this in proofs going forward. It'll be written out just like this, or with abbreviations too, which I'll show you later. If 2 what? Now what is given to us? Well, K and M is given to us after our if K is parallel to M. So if 2 parallel lines are cut by a transversal, then what? What's the conclusion we can make? Then corresponding angles are congruent. And I give this to you now, and we leave this, and we're not going to prove it because it turns out we can't prove it. And we need to make an assumption about parallel lines first. This is an important thing if you study more stuff with geometry in the future. But this is one of the most famous things, is that you make an assumption and then you can prove a whole bunch of stuff. And this is the assumption your book makes, is that corresponding angles are congruent when you have parallel lines cut by transversal. So therefore, what is this going to classified, guys, as? And I've been building to this for the last 5 minutes or so. They're going to classify this because we're not going to prove it. It is make less and less of a big deal of it in the future, a postulate. That's right, friends, a postulate. Make sure you know the difference between, I know we're already in chapter 2, but hey, some people pay closer attention than others. Definitions, postulates, and theorems. And this is certainly a postulate because we're not going to be proving this one. So breaking it aside here, we'll start with our founding postulate here for parallel lines. Some books assume something else, which we'll prove later. Now that we have this assumed, we'll prove something else actually about angle 1 and angle 2. We'll do that later. But anyways, make sure you get this in notebooks, highlight it out. This is sort of our key postulate there for parallel lines. If 2 parallel lines are cut by a transversal, then corresponding angles are congruent. Then corresponding angles are congruent. So get used to this here. When you're using this, you're going to use this in proofs, right? If you want to say, what angles can we say are congruent if K and M are parallel to one another? We can say angle 3 congruent to angle 2. Congruent to angle 2. So then another corresponding. So remember, we got kind of position 1, 2, 3, 4, and then, right, these are both in position 2 right here. So corresponding is sort of like where the 2 lines meet. Right? Is it upper left? Is it upper right, lower left? And then this is upper right. So it corresponds to the upper right here. If they're parallel, then we're going to know that angle 3 and angle 2 are congruent to one another. And that's here. So get used to writing this. You're going to write this a lot. If I wanted to just jump into, if I notice this in a diagram, or if I've already established that K is parallel to M, then I can establish angle 3 is congruent to angle 2. And then I got to write this as my reason. If 2 parallel lines are cut in transversal, then alternate interior angles are congruent. Here's how that's a mouthful, right? I know you're just like, I got to write it all out now, put it in your notebooks, but then also put the abbreviation down, because I do let you abbreviate this when you're writing proofs. Hey, that's a good thing. And this is what you can abbreviate it as. This is how I abbreviate it, at least. If you don't abbreviate it exactly like me, then that's fine, right? I still get what you're saying, but you got to say the key stuff, right? You got to say 2 parallel lines, right? If you have parallel lines, that's fine too, because that implies that there are 2 or more. So if parallel lines, then core angles congruent. That's probably the shortest that you can actually write that down. And I get what you're saying. You've said everything you needed to say. So you basically just need to abbreviate and make it clear to me and clear to the reader. And any reader of geometry will understand what you're saying here. And making sure that after if part is the given premise of the postulate, and then after then part is the conclusion that you want to establish. So if 2 parallel lines cut by a transversal, then corresponding angles are congruent. So get used to this. Get used to this. You're actually going to write if 2 parallel lines cut by a transversal. That's actually going to be a given. So this hypothesis here, this is going to be the hypothesis of many proofs we're now going to prove in a second. Okay, so if 2 parallel lines are cut by a transversal, then corresponding angles are congruent. Interesting here. Mr. Fortin, I see angle 3, angle 2. That helps us out with the postulate, but wait, we have another angle down here. Why is that there? What do you think we can do now? Because it turns out we had to make one assumption. Angle 3 is congruent to angle 2 because we'll assume corresponding angles are congruent. So what can we do now? Let's see here. Considering that we assumed that the preceding postulate is true, right? It was an assumption, pretty safe assumption. Nobody's been able to disprove that at all yet. But what do you think we're able to do now? Right? We assumed that corresponding angles would have to be congruent. Yes! Oh, I'm so excited. This is good. We finally got to section 2.2. Can you hear my voice? I'm excited. That's right. I'm excited. This is it. I live for this. Is that sad? I don't know. No, it's exciting. Prove lots of theorems. That's right. We can prove lots of theorems. Just starting with this, that this is congruent to that. Hey, I think we could say something about angle 1 that we knew it was congruent to angle 3. But what else do we know? That's what we want to get to yet. So prove lots of theorems. Yes, we're excited. I got the fireworks going off here. I got my squirrel friend here is pumped up. Let's freaking do it. Let's do it. You excited? Yes, you are. I know you're so excited. Anyways, so I said it a minute or two ago, probably more like 2 minutes. But get used to this. Get used to seeing this opening statement here, this hypothesis, this if statement here, this given premise of now what is going to be a theorem here. It matches the given premise of the postulate. If two parallel lines, okay? So if K is parallel to M, that's your given, then right? You're able to assume that angle 3 is congruent to angle 2, but now you're able to prove what? Based on that assumption. That's right. Alternate interior angles are congruent. Write it down. Write it down. I'll give you 10 seconds just to write that down. Very important. Give you some peace and quiet. Give you some space. Writing it. Please write it. All right. If two parallel lines are cut by a transversal, then alternate interior angles are congruent. Okie dokie, right? We knew that angle 3 is congruent to angle 2. How? Well, we're not talking about that, right? We're actually talking about angle 1 and angle 2. So remember, in the interior means the interior of the two lines that are cut by that transversal. So clearly here, line T, because it's the one that does the intersecting of the two lines, that's the transversal. So the interior is over here. We got 1 angle, 2 angles, 3 angles, 4 angles, and these two angles are congruent. And these two angles, these unnumbered angles right here, but I referred to them as angle 2 and angle 4 a second ago, they would be congruent too, and we can prove all that. But the big thing here is hanging out in our diagram is angle 3, because that's what's going to get us there. So we'll talk through it real quick, and then we'll write a 2-column proof. Basically, just what we talked about now, because I think I have faith in you. I bet you can prove this on your own. You don't need to listen to me, do you? But my question for you is this, just to point it out, because my job is to hopefully illuminate things that are hard to see, because it can be hard to notice stuff if you don't have somebody pointing it out to you all the time. Although I do want you to think through it and see it yourself. That's the goal. But anyways, we got angle 3 right here. Okay, so I wrote here, angle 3 is congruent to both angle 2 and angle 1. So that's nice. That's a nice fact that you could establish. Angle 2 is congruent to both angle 2 and angle 1. That almost gets you there to saying that angles 1 and angle 2 are congruent to one another. So I think you know what you have to use as a step there. Two things both congruent to the same thing are, we'll get to that later. Anyways, angle 3 is congruent to both angle 2 and angle 1. Why? Well, let's start with angle 3 and angle 2. Why are they congruent? Somebody tell me. I'm calling on you. Everybody, you have to say at least 2 things a week out loud in class. Let's see what we got here. Angle 3 is congruent to angle 2 because, that's right, if two parallel lines are cut by a transversal, then we make the assumption that corresponding angles are congruent. The postulate, right? The postulate we just did. We needed to introduce that because now that's going to help us prove that these alternate interior angles are congruent. And we know that angle 3 is congruent to angle 1. We knew that from back in chapter 1. And maybe you knew it from middle school too, that vertical angles are congruent. So you'll use that. Vertical angles congruent here, corresponding angles are congruent here. So if this is congruent, that is congruent, and then we can join these two. Those are congruent. I think you know what step that is. I know I have to do a lot of practicing of that sort of three-way there congruency thing step there, because a lot of people say substitution. It's not substitution. Anyways, given here, we have, again, given premise, if two parallel lines are cut by a transversal, you don't have to write this like transversal part there. If you're writing this proof, just write this and then just draw it. We can see that there's a transversal T cutting K and M. But anyways, given two parallel lines cut by a transversal, then the angles featured in here, these alternate interior angles, they're going to be congruent. Angle 1 congruent to angle 2. And you'll use this in proofs of funny little diagrams. We'll have alternate interior angles, and you're going to want to say that they're congruent there to one another when you do other proofs for your homework. Okay, so Dwight is excited. Dwight from the ICE office is excited. The squirrel's excited, and I'm super excited. You've been able to tell that though, right? You can kind of hear me through your computer screen, your phone screen. You can just feel the energy and the excitement. Anyway, step 1, again, 100 points. Perfect score on your next test. First person to tell me what step 1 is. Oh, yes, you got a perfect score on the next test. A given, right? That's all I do, right? Write the given statement, you get 100. Okay, I'm just for full disclosure, I'm just joking. You don't get 100 just for saying given, but you do get points for writing given. That's good. But you can do the rest. You can do the rest here. Okay. Anyways, we got parallel lines. That's good. So when we talk about parallel lines, what's something that connects to? What's something that we just learned perhaps that can get us from parallel lines to then making another statement that we accept as a rule or as a fact? Yeah, we can say angle 3 is congruent to angle 2. Why can we say that? Why can we say that again? Practice it. How am I going to abbreviate it here? What am I going to write? If two parallel lines are cut by transversal, so here's how I abbreviate it, then corresponding angles are congruent. Remember, is that a postulate or a theorem? Because the book will come back, and I will come back too, to be like, what was the assumption we had to make here? Because we did one of these facts we'll learn today is an assumption. It's not even a fact. It's a rule. Yeah, this is the postulate. This is a postulate. Corresponding angles. We needed to start with assuming corresponding angles were congruent, and now we're trying to prove that alternate interior angles are congruent. Okay? So next step is we probably want to say angle 3 is congruent to angle 1. We already knew that there, and then the reason for that is vertical angles are congruent. And then, hey, I've been talking about it a lot. You're sure, like, I get it. Like, this isn't that hard. Two things equaling to the same thing or being congruent to the same thing are congruent to one another, and that's what property of congruence. The old transitive property of congruence. And hooray, we got there. Transitive, again, just reminder transitive, right? Angle 1, angle 2, we have a common thread. They're both equal or congruent to angle 3, therefore they must be congruent to each other. They both represent the same size angle, right? Angle 3 is basically the same angle as angle 2, and angle 3 is basically the same angle as angle 1, so these two are basically the same angle, or they have equal measurements, and therefore are congruent to one another. You notice this little 3-dot thing that I put there? Don't worry about this. I put this on some proofs, but hey, does anybody know what the 3-dot? This is a symbol, actually. When you're writing a lot of math or writing something, this is an accepted symbol to abbreviate something. I put it at the end of the proof, too. Okay, so proofs are actually kind of written as if kind of then statements and justifications. So if I actually read my proof here, if we have parallel lines, so if K is parallel to M, then angle 3 is congruent to angle 2, and then angle 3 is congruent to angle 1 because vertical angles are congruent and because what we set up here. And then I have this other symbol down here. So here, if, and then because, and finally, well, it doesn't stand for and finally, it stands for something pretty close to something. This symbol, ... stands for therefore. Okay, therefore. Therefore, angle 1 is congruent to angle 2 because of the transitive property of congruence. Okay, so I know these proofs can look pretty confusing or can look like, why do we do this? What the heck is this? We do this because this is just an organized way of establishing facts. And I mean that because you could prove this by writing something called a paragraph proof, but basically what you have here as far as a proof here is a more organized way to write a paragraph proof. What do I mean by paragraph proof here? Well, if you didn't catch what I said earlier, these are pretty much, I can read out what this proof is in kind of more normal English, which I'll just do to kind of demonstrate. You don't need to worry about it for right now. But if I read out this whole proof, you should see a full justification getting us from the beginning to the end. So if I read it, I could say, if K is parallel to M by given, then angle 3 is congruent to angle 2 because if two parallel lines cut by transversal, then corresponding angles are congruent. Then angle 3 is congruent to angle 1 because vertical angles are congruent. Therefore, so the 3 dots was therefore, angle 1 is congruent to angle 2 because of the transitive property of congruence. So see what I did there? I just inserted some words, if, then, because, and therefore, right in between all the steps that I've been saying. So it's one way to quickly kind of go through and read to make sure you've said everything you needed to say in order to prove what you want to do, which is getting from step 1 to step 4 and getting us to a theorem. So here we have a theorem. If two parallel lines are cut by a transversal, then alternate interior angles are congruent. Okay, so now when we start with this, we can immediately say this. We have two parallel lines. We can immediately say alternate interior angles are congruent because we did the work, right? We proved it. We went through the work. We started with this, and then we said that, and then we said that, and now we can assert this. So we can skip saying those every single time, and we can just say that alternate interior angles are congruent. So when you have a diagram and you know things are parallel, sometimes you just want to mark up alternate interior angles are congruent, or you want to mark up that corresponding angles are congruent and whatnot. Anyway, next one. So we have another theorem here. We were not going to prove the next theorem, but it's just as important as the last one. You're going to prove it. And the exciting thing here is you're going to prove it when you do number 19 on tonight's homework. Okay, so we'll be able to talk through it, and you'll realize and hopefully accept that it's true here. Yes, Dwight from the office is very excited again. It says here as a theorem, if two parallel lines are cut by a transversal, we can say something else. So again, get used to this. If two, right? I usually write the letter number 2 and then parallel symbol lines cut by trans. Then let's see what the diagram is suggesting us here. Okay, so here we have two parallel lines. And line K is parallel to line M. Okay, we'd be able to say that angle 1 and angle 2 are congruent. So what's being suggested here? Well, angle 4 is supplementary to angle 2. So what can we say about 1 and 4? Let's see here. If two parallel lines are cut by a transversal, then my guess is we're going to talk about a special transversal angle relationship here. So we're not going to talk about 4 and 2 because those are just those make up a straight angle, right? They're two parts of a straight angle. So that's something from chapter 1. We're not going to talk about alternate interior angles. So we just talked about those. So we're going to talk about these. Okay, we're going to talk about angle 1 and angle 4. So then same side interior angles. Okay, so we can write a proof regarding angle 1 and angle 4. What do we have to know about angle 1 and angle 4? So if two parallel lines are cut by a transversal, and I want to slow down now because this theorem is just as important as the last one. If two parallel lines are cut by a transversal, then same side interior angles are what? You'll get used to saying this. They are supplementary. Yeah. So when you write this proof here, obviously angle 1 and angle 2, they have the same measurements. Angle 2 plus angle 4 is 180 degrees. So by substitution, right, we can just say measure of angle 1 plus measure of angle 4 also equals 180 degrees by substituting measure of angle 1 for measure of angle 2 after you say that these two add to 180. So that's basically the proof. I wanted to just kind of talk back through it real quick. So when you get to this, sometimes, and it's also too, we haven't been doing the book very long. Sometimes we'll talk about a theorem, you're supposed to prove it. And I show you this stuff here because it says, it'll say in number 19, prove this theorem. We'll just say prove this. It'll write this out, or it'll say prove, and it'll give you the number in the book to find it. But then you have to come up with the given statement and the proof statement on your own, and the diagram. Okay, so I show this to you because when you do number 19 tonight, you can just use my diagram, and you can just use my given and my proof statements here. You're welcome to try it, come up with those on your own, right? That's fine too, but sometimes it can be hard to just reading the theorem and realizing what diagram you need to draw and what the given and the proof is. Okay, so it's pretty clear here. You need to draw two parallel lines and a transversal, and then also label the same side interior angles, but you might forget, oh, I should label my alternate interior angles because that's how I'm going to get to proving this. Okay, so when you do number 19 tonight, just use this diagram, use that if you have trouble on it at all. All right, so I think this is the last one. I could be wrong, and then we have some oral practice after that. But it says here, predict the next theorem, which uses the given diagram below. Okay, uses the given diagram. So this is given to you, and we're going to say a related theorem related to what we've seen so far. So here, look, I'm going to have you come up with the ifs then. And then I'm going to have you decide what could possibly be proven here. So let me break this down a little bit for you. We're going to try here. And it says ready, set, go, but maybe we don't need to go right now. It says, what does the following diagram tell us is given? It's our given diagram. So all of these are given premises that are marked down. And then it says, what do you think we can easily prove? Okay, so think about it, come up with the given, and then think, what can I now say? What can I now say to prove here? Ready, set, go. 20 seconds just to think about it. Quiet think time. Ready, set, go. Ten seconds. 5 seconds. 3, 2, and 1. Okie dokie. All right, let's think about what this is helping us prove here, because this will come in handy for us to use in proofs in the future. But given, pretty obviously here we have givens. What'd you get for given? Pretty obviously here, L is parallel to N, that's for sure. Okay, so L is parallel to N, but then we're given one other thing, just one other thing, not two other things, we're given just one thing. So L is parallel to N. So if L is parallel to N, and L is what? L is perpendicular to T. Okay, so L is perpendicular to T. What do you then think we can prove? Okay, let's put in our given here. We got t. Okay, so t is perpendicular to n. So t perpendicular to L, t perpendicular to L, and L parallel to n. Then what do you think? We haven't said anything about line n really, or another thing we can say about line n. Well, line n is also going to be perpendicular to t. There we go, right there. Okay, there we go. So notice this here, right? So the way that I point this out when you're going to use this in proofs in the future, or just kind of like what replaces what. Here, t is, so t on underline t is perpendicular to L, and then L is parallel to n. So n could go in for L right here. Think about it that way. Think about it kind of that way. That's kind of confusing. I don't know if you do it that way. But here, L is parallel to a line, and L is also perpendicular to a transversal. Therefore, that line that L is parallel to is also perpendicular to that transversal. We're gonna have to clean that up when we put it into words here. That's messy. Sorry guys, I think it kind of led you to more confusion than actually getting it up here. But anyways, the goal of this is that you basically have three lines. Think about it as this: you have three lines. Two are parallel. One is perpendicular to one of the lines. You can make the conclusion that that line is also perpendicular to the second parallel line, right? It's the second parallel line. So this is just going to help us when we have many parallel lines and we know that one line is perpendicular to one of those parallel lines, then it'll be perpendicular to all other lines that are parallel to that original line. Does that make sense? I don't know. It's wordy. Some of these geometry theorems are wordy, so hopefully it makes you a better reader and more attentive to the things you need to pay attention to. But anyways, this is how the book words it. Let's just go ahead and read it rather than having you kind of word it out. Let's read it together. It says here, if two parallel lines are cut by a transversal, and the transversal is perpendicular to one of them. Okay, so I think they're already kind of writing this better than I was kind of talking about a minute or two ago. But if two parallel lines are cut by a transversal, and the transversal is perpendicular to one of them, then what can we establish? Well, right, we would know parallel lines here. Well, if this is perpendicular, then this has got to be a right angle, right, by definition of right angle. And this has got to be 90 degrees. So this also has to be a right angle in 90 degrees. Therefore, this also has to be perpendicular. So then it is perpendicular to the other line also. By other one, they just mean the other one of the two parallel lines. Okay, so to read it again, to write it in your notebooks, right? Always keep all your theorems in a safe place because you end up using them. And again, if you don't know the exact wording of it, don't worry because you're not going to forget, right, the whole thing, right? You'll be able to describe it, and that's fine on the test or on homework. As long as you are pretty close to wording this, totally fine. If two parallel lines are cut by a transversal, and the transversal is perpendicular to one of them also, then it is perpendicular to the other one also. And then we're good to go. Okay, so let's do this. Dwight's excited. He's like, we haven't proven enough, guys. We haven't proven enough today. So let's get this freaking proof done. And we got it set up here. And we got our proof, statements, reasons. So Dwight's gonna be very excited. Let's do this. Step one, and again, you don't get 100 just for doing that, but you do get some points. So step one is, let's say a line perpendicular to another line, and then that other line is parallel to another line here. And we want to say that line T is perpendicular to line N, right? So basically we're just trying to replace L with N here in this statement. And we can do that because of, I think, an angle relationship that we assumed earlier. So let's maybe start with that. So we have angle 1 and angle 2 listed here. And we can say angle 1 and angle 2 are what? Congruent to one another. And I went with angle measurements here. So when you are trying to say corresponding angles are congruent, that's what you're doing here, right? You're doing if two parallel lines are cut by a transversal, then their corresponding angles that get formed are congruent. So that is congruent to that. And I went with measurements here because my next step is this. Measurement of angle 1 is 90. So anyways, so a lot of times instead of writing that angles are congruent to one another, it's easier to say that their measurements are equal to each other. And that's okay. You don't need to say definition of congruent there. You can just use this, right? Congruent angles have the same measurements. It's fine. You don't need to write down definition of congruent angles as the reason. So anyways, writing it out this way is easier because step 3, I'm going to have to write this. Measure of angle 1 equals 90 because this is an equation. So if I put angle 1 is congruent to angle 2, that's not an equation. That's a statement of congruency. So anyways, if I know that I'm going to have to do something with equals later, then it's just better to put things with equals in. So I would recommend instead of using the congruent symbol, just in general, using measure of an angle equals the measurement of their angle when you're talking about right angles. Anyways, we'll get back to that later. Step 3, I do this with step 3, and you might be wondering why I'm allowed to get away with this. Okay, so we've talked about the parallel lines in step 2, right? Parallel lines gets us to that. These angles have the same measurements. We haven't yet talked about the perpendicularness here, okay? But I broke this down into one step. So from step 1, T is perpendicular to L. Therefore, T is perpendicular to L. Therefore, all these angles have got to be right angles by definition of perpendicular. And then, but I didn't write anything about right angles. I wrote measure of angle 1 equals 90. Why can I do that in one single step? I'll review this afterwards too. I can do that because I combine steps. That's right, I combine steps. So look here, in my reasons, I put 2 reasons down. So this is the way, and I know I've gone over this with you once before, so I'm going over it with you again because I want you to do this because this saves time on proofs, is that it actually takes 2 justifications to justify you have perpendicular lines. Getting that to being 90 degrees takes 2 steps because perpendicular lines form right angles. What is that? That's the definition of perpendicular lines. If you have a right angle, then that measurement of the angle is 90 degrees. What is that? Well, that's the definition of right angle. So to get from perpendicular lines to the angle measuring 90 degrees, you need to use both reasons because that's how it's been written out for us and set up here earlier in the book. We're following those rules because we want to see what follows from that and what we can prove from that. Okay, so anyways, measure of angle 1 equals 90. And then therefore, I can also make the conclusion that measure of angle 2 equals 90. And the reason for that, what's the reason for that? Well, I see measure of angle 1 happening twice here, and then these 2 things equal that thing. So that's also transitive property of equality. So measure of angle 2 also equals 90. So you see what I'm doing here? I put the 90 in because because these are perpendicular, I can get to 90 degrees here. And then since these are equal, I can get to 90 degrees here. And now that I know that angle 2 measures 90 degrees, what can I say next? Well, 2 lines meeting at a 90-degree angle, they're going to have to be perpendicular to one another, which is what I'm trying to prove. Okay, and because in step 4 I said measure of angle 2 is 90 degrees, that fits the definition of right angle, right? A right angle has 90 degrees worth of measurements. That establishes this as a right angle, but that's not what I say in step 5. What do I say? Well, because this is a right angle, that means that it forms perpendicular lines, definition of perpendicular lines there. So again, I'm using 2 reasons here, right? Part of the reason why they have this proof here is because they want you to start doing that, collapsing some steps of a proof. So instead of writing out, you could have totally written in step 5, angle 2 is a right angle, and then step 6, T is perpendicular to N, but you guys want to avoid the work, right? You want to avoid the tedious work and just say what you need to say to show that you know it. And so therefore, we have 2 steps there. Going from step 4 to step 5 requires 2 reasons: definition of right angle, definition of perpendicular lines. Okie dokie, so we got there. So guys, now in the future, right, we get something like this. We'd say as a given premise. We already proved, right? We justified this each step along the way. We gave our reasons along the way. So now we can go directly to saying that that one transversal was perpendicular to one of 2 parallel lines. Well, it's going to be perpendicular to the second parallel line as well. And we're good to go with using this as a theorem here. Does it have to be worded exactly like this when you use this reason? Say if you wanted to go from step 1 to 5 directly in the future and you wanted to use this theorem, no, you don't have to word it exactly like this, but you just have to be able to describe it well enough, right, where it's fairly accurate. Right? If we have parallel lines and transversals perpendicular to one of them, then it's perpendicular to the other one also. So pretty quick, right? Pretty quick, and it's going to be super accurate. But what I just said there was also an A+ way of presenting this theorem. Okie dokie, so here is the thing that I was doing on the last slide. I was trying to stress to you guys once more. I know I've talked about this another time in chapter 1 with you guys, but and this is also written in chapter 1. This is also in case you missed it, right? In case you weren't paying attention here, or in case you haven't been doing this, start doing it, right? Start skipping these steps. If more of us understands that you can skip a couple steps, the easier it is to be writing some of these proofs in the future and saving us some work and saving us some time on stuff here. So this is our side note here. You should have read about this in chapter 1 about combining definition of perpendicular lines with the definition of a right angle into a single step of a proof. You're allowed to combine steps as long as it's an obvious thing to do. Okay, so they write a bit about this here. right? So it says the level of detail to include in proof may differ from person to person. And it says as you gain more experience writing proofs, you and your teacher may agree to what steps may be combined or omitted, right? Omitted means skipped or omitted, left out. So sometimes we don't need to say absolutely everything in a proof. And you and me being your teacher, we can decide that here. So this is one thing that we're deciding right now instead of writing out, right? So to get from perpendicular lines, right? If ray BA is perpendicular to ray BD, that would technically require 2 full steps to get to that measurement measures 90 degrees. Right? First, we'd have to say they're perpendicular, and then we'd have to say that they're 90 degrees. But we can just lump that into one step, okay? By just knowing that we are using 2 reasons to get from perpendicular lines to 90 degrees. Okay, and that's it, right? I'm not going to lecture about that anymore, so hopefully you're sick of it now, and you'll just start doing it and get it good to go in the future. All right, so we're done with theorems. Right, we're done with theorems, remember, and proofs and postulates. Right, we're done with all that stuff. Just oral practice for a minute, and then you'll go into your homework after this. So remember, what was the postulate for today? See if you can just kind of remember and commit yourself. Look down at your paper. Right, do you have good notes today? What's the postulate? Well, if 2 parallel lines are cut by a transversal, that's how a lot of the theorems began today and postulates began today. What was the assumption we made then? Thank you very much for raising your hand. And corresponding angles are congruent. Okay, and then we also had theorems for those 2 parallel lines that got us alternate interior angles being congruent. And then in those 2 parallel lines, we can also say that same side interior angles are what? Are supplementary, right? Not congruent, but supplementary. And then finally, right, as sort of a follow-up to corresponding angles being congruent, we have parallel lines. We could also say that if we have a couple parallel lines and then a transversal is perpendicular to one of them, it'll be perpendicular to the other one also. Okay, so just make sure you're going through that again in your own heads or along with me. You're saying it out loud is really going to help you out. And all these will be things that we'll have to use to get to some other stuff in the future. But anyways, let's practice it on out here. We're looking to justify it. I'm going to call on someone at random. You might roll the die, give you a minute to think about it, and talk with your groups. Obviously, you're not doing that if you're just watching this video. But anyways, it says here, find the measure of angle PQR and justify our reasoning. Okay, we got to give our theorem or postulate or whatever. There we go. Ready, set, go. You got 30 seconds. Find the measure and justify. Give me a reason. Ready, set, go. Ten seconds. Measurements. More importantly, the reason. We are rolling it down. I'm calling someone random. I'm calling on you, Maxwell. What are you saying here, Maxwell? There we go. 90 degrees. Okay. All right. Yes, I agree. Measurement angle PQR, 90 degrees. This is perpendicular, right? It's a right angle. It's 90 degrees. So this has got to be 90 degrees also. How do I know that? Well, the transversal is perpendicular to RS, and if it's perpendicular to one of 2 parallel lines, it's perpendicular to the other parallel line also. Okay, so if you word it out like this, totally fine too. Okay, let's practice a little bit more here. Find the values of x and y. Okay, so here it's going to involve like theorems and postulates, things we know that are true about specific angle pairs, and it's going to have you use some algebra using the ideas of equal measurements, knowing that they're true, doing some algebra to solve for x and y. So find the values of x and y in this diagram. Ready, set, go. You do 1 minute. Less than 1 minute. 30 seconds to go. Seconds. You can get this pretty quickly, actually, I think. Right? But we go at different speeds. 7, 6, 5, 4, 3, 2, and 1. All right, I think what's easiest, well, they're both pretty easy. What's x? Yeah, x is 30, right? They're corresponding angles right here. So 2x equals 60. And so therefore 1x has got to equal 30. Okay, then y, what's the relationship between y and 60? Well, these are parallel lines, and then these would be same side interior angles. Look, this is a transversal here for these 2 parallel lines. So these would have to add up to what? 180. So 180 minus 60, 120. And that is that, okay? Justification, because the lines are parallel and then the angle pairs are corresponding. So here, parallel lines. Line C is a transversal, so these are in corresponding positions, right? This sort of top right of these four and the top right of these four. So 2x equals 60. And then the other one here, right? Two parallel lines, right? Harder to see because it's over here. Top and bottom are easier to see parallel lines. But anyways, these are still parallel, and line B is our transversal. Okay, line B is our transversal. So this here are same side interior angles, right? Same side interior angles. And that means that 60 plus 180, sorry, y is supplementary. So they add to 180, so that means y equals 120. And x equals 30. So we would just divide both sides by 2 here and subtract 60 from both sides here, getting us from 180 down to 120. All right, more oral practice. I think this might be the last one, last slide, but there are 3 questions remaining. So let's do this. I'm just gonna point. I'm gonna point somebody and call you. You, sir, you, sir, yes, you're on. Angle 2 congruent to angle 4. Why do we know that? Why do we know that? What are the relationship? What's the relationship here? So given, okay, so we have here 2 parallel lines. It's given to us. B and C are parallel. 2 and 4. Okay, 2 and 4. Well, they're in corresponding positions. So if 2 parallel lines are cut by a transversal, then corresponding angles are congruent. That's the reason you're writing for given for a proof if you're writing that angle 2 is congruent to angle 4. That was an assumption. Okie dokie, next one here, a little bit trickier because this will require, I think, 3 justifications. Ready, set, go on this one. Measure angle 3 plus measure angle 5 equals 180. How would you make that justification? What would you have to connect with? What would you say first, second, and third? Ready, set, a go. And you, man, just sitting there in the back. You thought I wasn't going to call on you, but guess what? I am. All right, why can I say this? Why can I actually say that measure angle 3 and measure angle 5? So these are on alternate sides of the transversal, but they don't really have a relationship. This is an interior angle, that's an exterior angle. So there's not really a name for this, but we do know that they add to 180. And look at this, this is obtuse, this is acute, right? It makes sense they add to 180. But I know this because, well, measure angle 3, yeah, well said, young lady. Measure angle 3 plus measure angle 2, that equals 180 because, and I'd say in a proof, I'd say this, if 2 parallel lines are cut by a transversal, same side interior angles are supplementary, right? Right? Interior, supplementary. Okay, so if I'd say this first, but then I can also say measure angle 2 equals measure angle 5 because vertical angles are congruent. So now, since I'm talking only about equality here, right? Equality here, I can use the substitution property of equality, substituting measure angle 5 in for measure angle 2, and yes, because they equal each other here. And then I get therefore, right? This is the therefore symbol, right? Right, so we get a then and a then, right? And then this is a therefore, measure angle 3 equals measure angle 5 equals 180 by substitution. That's what we're trying to do. So hopefully you said something like that. The young lady in the back did as well. Finally, this gentleman in the front here, I'm just calling on you. I'm putting it up there. What's the relationship between measure angle 3 and measure angle 6? Well, here's a transversal. Are they the same side or are they alternate sides? Yeah, they're alternate sides. Alternates, and then they in the interior or are they in the exterior of the 2 parallels? They're in the interior, okay? Because alternate interior angles are congruent if you have 2 parallel lines cut by a transversal. It's okay if you write that way too, right? If your if part comes second, that's fine. That's fine. Justified. And that's that. Here's homework right here. So, I think these lessons, they just flow a lot better. You might be thinking, whoa, what the heck was that all about? There's a lot of stuff. But hey, that was a lot more fun for me to go through because we're proving things, we're getting oral practice, we're becoming solid geometry students. And that for me is very exciting. All right, so we got this one here. Try to get them all done. Again, don't spend too much time on the classroom exercises. Don't spend too much time over here. And then these might be a little bit harder, right? So spend 3-4 minutes on some of these problems. Givens, proof statements, draw diagrams over here. That's it for me. Section 2-3 will be pretty similar to this. We're going to be looking at basically, if we don't know lines are parallel, what are some ways we can figure out lines are parallel in the next section. So it'll feel pretty similar to this, which I'm excited for because I like this section. And that's it. Have a good practice, guys. Email me if you have any questions. Thanks. Bye.